it's really glad to have the chance to be invited here to present present and share my recent research on large language models. And the topic, as you can see here, is towards architectural efficiency for large language models. So basically, this talk will cover my recent research progress regarding how to reduce the computational cost of large language models. And recently, there's a rapid growth in academic interest in language models and the large language models, and also over recent years, if you measure this rapid growth with the cumulative number of archive papers containing the specific keywords, you can see there's a rapid growth recently. And there's a particularly steep rise following the release of ChatGPT. And also, besides the academic interests, there's many industry companies try to, they also spend a lot of efforts on large language models. And you can see from this figure, there's many large language models released by these companies like Google, Meta, and some other companies. And of course, OpenAI, I should not forget it. And also, at the first glance, there are more open source models. However, actually, most of these open source models only have model weights, and the training data and details are missing. You can also see that more and more large language models they are available after ChatGPT. So basically, let's briefly talk about the background of large language models and a little bit of history of the language modeling. So there can be, basically they can be separated into 4 stages. And in the first stage, we have a specific task helper, where there are n-grams models like focus on statistical methods for specific tasks. And in 2013, we have word vector and neural probabilistic language models. And they introduced the static word embedding and neural context modeling for natural language processing. And more recently, in 2018, we have transformable natural language processing task solvers. There are portraying models like BERT or GPT-1 or 2. They can produce context-aware representation with portraying the model plus a fine-tuning pipeline. And most recently, we have general purpose task solver. And there are large language models like GPT-304, ChatGPT, and Claude. And they emerge as scalable general purpose tools capable of solving different real-world tasks based on prompt-based completion. So here is a brief illustration for the technical evolution of GPT series models. Back in 2018, we have the most basic architecture for all these recent large language models. It is the GPT-1 model, and it uses decoder-only architecture with generative pre-training. And later we have GPT-3, and GPT-3 has some context learning capacity, and they also explore the scaling limits for these decoder-based models. And at the another line of research, they combine with instruction tuning with and also reinforced learning from human feedback to align the output or the response from large language models with human preference. And if you combine these 2 lines of research, one line is for a stronger pre-training model, and the other line is how to align this stronger pre-training model with human preference, then you basically have ChatGPT. And of course, ChatGPT is also become stronger and stronger. And lately they supports longer context window, and they also supports multimodal ability. Multimodal inputs. And recently, there are models like GPT-01, and they have reasoning capacities by involve mechanism like thinking. And in this figure, we shows a brief architecture of the large language model. And basically, the large language models consist of a lot of decoder block. And each decoder block has several components. And the first component is the feed-forward neural network or multi-layer perceptron layers. And also you have the self-attention layer and also layer norm for normalization. And for the feed-forward neural network or MLP layer, we have several other choices like mixture of experts or gated multi-layer perceptron layers. And you can also switch layer norm to other kind of normalization techniques. And of course, for self-attention, there's also other choices like group query attention, latent attention, and also you can even replace self-attention with a recurrent neural network. So if you look at this structure in a higher level, it is natural to treat the feed-forward neural network as channel mixing and self-attention as time mixing. So that's also the reason why self-attention can be replaced by recurrent neural networks. And so although large language models, they are very powerful, but their model size is also largely increased in the past several years. And also these large models brings many challenges. So firstly, they will have very high computational demanding, and they brings challenges regarding storage and memory limitations. And also, they can hardly be deployed on devices with resources constraints like your mobile phone. And overall speaking, it makes everything much more expensive regarding deploying the model or training the model. So we have basically to reduce the cost of large language models, we have two directions. One direction is we can try to reduce, reduce the training cost at the tuning time or like training time. And there are methods like parameter efficient fine tuning where they try to reduce the number of trainable parameters in the model so that the training cost can be largely reduced in terms of the memory cost. And we also have other techniques like weight pruning, weight quantization, knowledge distillation, or other techniques to reduce the model size for inference. And the key takeaway here is that training costs usually are much higher than the inference cost if you only think about one sequence. However, training cost, it's a one-time cost. But inference cost grows linearly when you have more and more requests from the users. So the inference cost will create bottleneck when you try to scale up your model to serve more people and provide more services. And this is the reason why reducing inference cost is sometimes more important and more practical. And so through this talk, we will mainly study how to reduce the inference cost. And the outline today is basically can be separated into these three parts. Firstly, we will talk about some initial attempts with singular value decomposition. And then we will talk about structure pruning for large language models. And in the last part, we will briefly talk about a mixture of expert models. So large language models mainly contain linear layers, and this makes singular value decomposition a very favorable choice for language models. So given a linear layer, as you can see in this figure, its weight matrix can be approximated by two smaller weight matrices from the result of singular value decomposition. And then by removing smaller singular values from the result of SVD, we can convert large linear layers into two smaller linear layers. And ideally, we want these two small linear layers have a smaller total number of parameters than the original linear layer. And This figure shows gives the overview of of our forced method or forced attempt on try to reducing the number of parameters of these language models. And here we take self-attention as an example, where it has query, key, and value weight matrices. So the figure below here, they are the regular singular value decomposition methods. And for these methods, they assume all the weight matrices or all the operations have the same number of ranks. So basically this assumes that every operation or every layer they have equal importance. And we think that this is this could result in suboptimal performance since you make everything uniform. And our method uses a module or like a neural network we call hypernetwork to produce top K like mask to control the number of ranks. And different operations here can have different number of ranks. This also means that important operations or important weight matrices will be allocated with more parameters or a higher number of ranks adaptively. And in this figure and table, we show the performance of our method compared to other baseline methods. And the FWSVD is just a previous state-of-the-art methods for language model compression using singular value decomposition. And a very straightforward observation is that under the same compression rate, our method called adaptive rank selection, it has a higher accuracy. And also they had achieved our method achieved the same accuracy with a smaller model. In the table below, we further try to apply our method on the Llama 7B model. Llama 7B is a is an open source model released by Meta. And from the table, you can see that the ARS method outperforms the other comparison baselines in terms of the average task performance. And in this experiment, we try to reduce around 75% of parameters of the original model. And our method is even able to outperform LLM Pruner, which only reduce half of the model parameters. But here, actually, we did not have a fair comparison, since LLM Pruner is not fine-tuned. But our model is fine-tuned for giving some tokens or giving some test. And here we have a short summary for the singular value decomposition based methods. And firstly, it's always very easy and straightforward to use, and you don't even have to change the model architecture. And also, it benefits a lot from using global allocation of ranks instead of using uniform ranks across different layers or operations. But the problem of singular value decomposition based method is that if you want to scale up, SVD brings huge burden since it introduces additional parameters. And if you look at the example below, where we try to decompose the original weight matrices by using singular value decomposition, it makes it to two. It will has like two resulting weight matrices. And these two resulting weight matrices will double the number of original parameters in the model. And this means that if you want to compress 10% or reduce 10% of model parameters, you need to reduce basically 55% of ranks within the model, and which in my understanding is very unreasonable. So facing this problem, we also try to further solving this problem by using structure pruning method. And compared to single value decomposition method, the largest benefit of structure pruning is it does not add additional parameters. And an example of structure pruning is LLM pruner. And for structure pruning, it just removes the whole column or rows of from the original weight matrices. And also you need to respect some connections within the model so that the model can function normally after pruning. And in short, LLM pruner groups connected weight vectors into one group, and it puts the group based on the importance score of this group. So, however, there's problem for existing structure pruning methods like IRM pruner. The problem is that the put position after structure pruning, they are restricted by the residual connection. And the residual connection is widely used in, basically in all the large language models and even in the other kind of models. And this reduces the flexibility of structure pruning. So basically, to relax this constraint or relax this restriction, we propose our own method, which we call it dimension independent structure pruning, and we allow free changes or free put positions across the input and output dimension of the weight matrices in like this is MLP block. And we use index operations to allow, to remove such dependency of pruning. And in the left figure, we have the overview of our method. And basically, we try to compress the input dimension and output dimension of the self-attention block, and also the input, output, and the middle dimension of the MLP block. So we propose this display IRM to maximally explore the design space of structure pruning, since you relax the constraint, and it makes the whole process much more, whole search space or design space of structure pruning much more flexible. And we also use index selection and index addition operations to avoid the dependency of the pruning positions. And we also, lastly, we try to use differentiable search to optimize this very large search space or design space. And in the table here, we compare our method with other state-of-the-art like structure pruning methods for several public large language models. And across all these benchmarks and pruning rates, our method has always has the best performance. And we test our method on several public models like Llama model released by Meta, and also Phi models released by Microsoft. And we also made some visualization to show the why our method is successful. So firstly, in this figure, we visualize preserve and put the model dimension or hidden dimension across different layers of the model. And a very simple and straightforward conclusion here is that every hidden dimension or model dimension is important. So you should not remove any of them, since across all these dimensions, there's on average there are 80% like occupation rate or preserved rate. And in the figure below, we shows the model structure of across different blocks. This is for Llama 2 7B model when removing around 50% of parameters. And you can see that the model structure, they are highly non-uniform. And this also corresponds to the observation from the single value decomposition based methods. So here's a short summary regarding structure pruning. Firstly, non-uniform sparsity allocation is still important, which means that different operations or different weight matrices, they should have different importance. And also, structure pruning is usually stronger than S3D-based methods if they compare them fairly. And also, we should not reduce the size of the model dimension, which is also the key to achieve good performance. And we suspect that this may be cause a phenomenon called superposition. So one way to explain why our methods have good performance and why reduce the model dimension is harmful is a concept called superposition. And what is the model dimension? It's actually the size of the residual connection in our method, or it's just the hidden dimension of the original dense large language model. The superposition is a phenomenon that models can represent more features than they have dimensions. If you look at the figure here, the example here, we have a two-dimensional space, and in the most extreme case, we can actually represent 5 features, which is much larger than the number of dimensions you have. If we put more formally, we can use it, Jason-Lindström's lemma, and where here f is a linear mapping from r large n to r small n, and m and n here they have an exponential relationship. You will adjust some points from a set x with m points. So if we think m here as the number of features and n as the hidden dimension or model dimension, and this means that if we decrease n, then we lose potential features in an exponential speed. This is because the relationship between m and n. And in addition, residual connections accumulate outputs from all these previous layers, which could make this problem much more severe. And there's already some set proof of superpositions in production level large language models, like the Cloud3 Sonnet. They apply a sparse autoencoder to residual connections in the middle layer of the model. And they discover the many interesting features within the model. And an example is the Golden Gate Bridge. And these features appear both in the text and also the images. This set proof regarding the superposition phenomenon. So the sparse autoencoder is just a model try to project inputs to a high-dimensional space. Remember that in the superposition setting, we have more features than the dimensions. So basically, this high-dimensional space try to have the same dimension and try to have the dimension equivalent to the number of features we have. So basically, each hidden dimension can represent a single feature or single semantic or have a single semantic meaning. And we want to find interpretable features in this high-dimensional space. And lastly, we will just briefly talk about the mixture of expert models. So I believe maybe some of you already know that DeepSeek models, they are actually very popular recently. And especially DeepSeek R1. And DeepSeek R1 achieves very strong performance compared to commercial and closed source models like OpenAI O1 model. And another interesting point of DeepSeek R1 is that it is much more cost effective. So according to some statistics, actually DeepSeek R1 is 25 times cheaper than OpenAI O1. And one of the main reasons here is because DeepSeek V3 or DeepSeek R1 models, they use mixture of expert text structures or architectures. So here is a very short explanation of mixture of expert models. Basically, you have an input, and it's just some matrix or vectors. And each input vectors will be assigned to the number of active experts out of the number of total experts by using a loader. And the layer's output is just the weighted sum of the outputs of the selected number of active experts. And each expert is just an MLP layer or a feed-forward network layer. And the MOE layer is actually a drop-in replacement of the MLP or feed-forward network layer. So why we want to use MOE? And as we saw in the DeepSeek example, we know that MOE can scale up to extremely large models without proportional increase in the computational cost, which means that the same, cheaper, of course. And also by activating only a small fraction of the parameters using these selected experts, MOE reduces computation they also maintain a very high model capacity. And from some existing works or research papers, they show that MOE models can always achieve better performance than dense models with the same number of active parameters, and they can often compete with the models with the same number of total parameters. Of course, there are some problems of MOE models, and they are very hard to train to begin with. And they often involve very heavy workloads to make the training really efficient, like you need to write some custom CUDA kernel and you need to do some hardware level optimization or something like that. And also, not every public released dense model has its MOE counterparts. So for example, Meta released like Llama 1 to Llama 3 models, and all these Llama series models, they don't have MOE counterparts. And facing these problems, we propose a solution where we try to convert these dense models to a mixture of expert models. And then we have this work, we call it 2MOE, and we try to converting dense large language models to a mixture of experts through dynamic structure pruning. And in short, 2MOE uses top-one loading for MLP layers and static and dynamic pruning along the high dimension for the multi-head self-attention layers. You can just, basically you can look at the MLP layer. Since this is where you convert the dense MLP layer to mixture of experts. Basically, we keep the original MLP weights and we use some mechanism to select the a subset of the vectors from these weight matrices, and we construct experts based on these selected weight vectors. And then we just repeat this process for all these n experts. And then we will have a model with a mix of experts layer, and we can replace it with the original MLP layer. So here are some results regarding our method, where we show the zero-shot task performance of compressed Llama 3 8B model and Qianwen 2.57B model without any fine-tuning. So you can see basically the MOE model has a lot, it can achieve a much better performance than the structure pruning baselines. And it has a much better utilization for the model parameters. And it can change the model architectures when loading to different tokens or to different inputs. And in this table, we visualize the assigned experts for each token or for each input. And different colors here just represents different experts. So generally speaking, there's not a very consistent pattern across different experts and different layers. But for the 16th layer, 16th MLP layer, we indeed found some pattern where the second expert with the blue color layer, they have many concepts related to number and to words related to math problems. For example, there are words regarding equation, line passing, and some similar words, and also many numbers are loaded to the second experts. So basically, the semantic meaning of our method of the resulting MOE model is still a problem that we need to study further. And then we'll have the summary for the MOE models. So we show that it is possible to convert dense large language models to a mixture of experts, and it has a major performance advantage compared to static pruning methods. Also, pruning to or converting to MOE model has a better chance to maintain the capacity of the original dense model. And of course, the experts may or may not have semantic meanings, which requires further validation. And lastly, is some future work regarding the architecture efficiency. So we want to have domain-specific models where we try to develop specialized models from general-purpose models by using techniques like pruning or convert MOE models to dense models again. And we want to this general purpose model works for fields like medicine, law, or other related fields. And we also want to have explain the pooling decisions of our methods. And we want to improve interoperability of pooling decisions using techniques like sparse autoencoder. And we also want to enhance the dense to MOE conversion by increasing the number of experts and the number of active experts to optimize the model performance. And lastly, we will try to scale up dense to MOE conversion, and we want to expand the total number of parameters while keeping the number of active parameters for efficiency. And that's all for my talk today, and thank you. And I'm happy to take any questions.
Thank you so much. But yeah, as you were saying, if you have any questions, we now just have some time for like a Q&A for Professor Gao, sorry. And then we also have some time for like a brief break before all of the student flash talks begin. So it should be beginning at 3, so if you wanted to grab some food, please feel free to.
Yeah, sure.
So I have 2 questions. First, on your structural pooling model. So how do you identify that which items are less critical for this model and ignore them? Are there certain metrics that you look into?
Basically, we use it's basically guided by the data. So we design some mechanism to make the pooling problem differentiable with respect to the loss of the model. So you can simply use the task loss of your own task to decide which components are important or less important. I mean, by formulating it as regularized optimization problem. Yeah, and it's totally differentiable. So I mean, you don't have to do anything on your end. Just let the auto differentiation package solve your problem, like PyTorch. Yeah.
Okay, I have another question on PyTorch and that. So we'll talk that later. But another question on the first approach where you talked about SVD approach.
Mm-hmm.
And because SVD is inherently, it's basically linear. So, and large language model, be it ChatGPT or any model that you saw earlier, they're all using nonlinear parameters. So do you think SVD is a good approach to infer the non-linear dynamics?
I mean, for nonlinearity, definitely SVD cannot, naively support nonlinearity in these large language models. Mm-hmm. So for SVD, we tried in our approach, at least for each weight matrix, it's still a linear, it's still doing linear multiplication with the input.
Right.
So for individual weight matrices, we can, apply SVD without any concerns. But there could be many trade-offs here because you can, reformulate the object of the SVD to incorporating like feature maps or other stuff into this process. So your SVD results could be better than the vanilla SVD. But definitely you need to do some research regarding this. But overall, from my understanding, SVD is not a very it's not a very capable approach in terms of compressing large language models, and especially there are many nonlinearities. You cannot merge like 2 consecutive linear weight matrices together and do SVD. That will be the most straightforward way to not be harmful to the original model capacity.
Thank you.
No problem. If there's no further question, I guess that's all. Yeah, thank you.
All right, thanks, Reagan, and hi, everyone. So I'm Akshay, and today I'm going to talk about how we can leverage machine learning and some fluid dynamics. By the way, anything that we breathe, I'm going to talk about the flow inside our body. So fluid dynamics, just a heads up. So we want to understand how we can leverage machine learning and this fluid dynamics to understand respiratory disease prevention, and that's for a large population. So think of a very complicated geometry, for example, an airplane. If we want to understand the precise flow physics of an airplane, what we need to do is we need to do a full-scale 3D computational fluid dynamics simulation, and we can understand the precise flow physics. We can bring the same concept to phase mask, and we can do a full-scale CFD simulation to understand how does flow behaves through the mask and through the gaps. So the problem with CFD is it's computationally very expensive. For example, to simulate one phase, it requires at least 5 days of computing power on 128 processors at HPC here. And I want to be the guy who can model not just one phase, but all the phases, because research has shown that even seemingly insignificant changes in your facial feature induce different leakage behavior. So I want to give you the best possible mask, not just for me, but to you all. And we have seen that breathing is enough for transferring or bioaerosol transmission. In fact, fun fact, breathing and talking are more dangerous than coughing and sneezing. And the reasoning is because when we breathe or talk, the droplets produced from our mouth is very small, and these droplets have tendency to linger in atmosphere for hours. So even when I leave home for today, my droplets will still be in this room. So if I'm infected, good luck to you guys. All right, so how can we leverage AI? So we use a stable diffusion model to synthetically create these phases using stable diffusion large language model. And these models gives us a 2D image. We can convert this 2D using another AI approach to 3D images. Then we deploy the mask using the concept of minimum elastic energy theory. The idea is that you deploy the mask and let the mask band to rest on your face until you reach equilibrium position. And then we do different fidelities of simulation. So first is low fidelity, which gives us an approximation that how flow behaves through the mask and through the periphery of the face. We can do mid fidelity, which gives a better results. And then we have full-scale CFD, which is, again, computationally very expensive. The advantage we have is because we can model thousands of faces, so we can infer some statistics and design the best possible mask, give those information to the mask manufacturer. So on the right side, I'm showing you some sample results. Here, what I'm doing is I'm simply transmuting just the facial feature nodes. So in one case, I have slightly taller nose, while in other case, I have slightly broader nose. And you can see even the leakage is predominantly more dominant across the nose region, but for this face, we see some leakage coming from the cheek region as well. And when we place the nose clip, like the N95 mask, you can see the leakage is now not dominant from the nose, but it gets redirected through the cheek region of the face. Now, breathing is just a part of picture. Things become more complex when person starts to talk.
Or wearing an unfitted surgical mask. These conditions simulate everyday situations where a virus could potentially spread.
I don't know what's going
As
on.
seen in these examples.
Don't know if the system gets so excited at my research. So things become more complicated when we start to talk, and the reason is as soon as we start to say hello world, our lip profile varies over time. And now, thanks to the deep learning algorithm that we could leverage, we can basically give a static face and any speech signal, for example, hello everyone, our model can generate dynamically talking message, as you see in this animated movie, and then we deploy the mask, and now we can show a complete pipeline here that now the person is talking, and we can look at how the gap profile, for example, how lip profile modifies when you say hello world, or when you say thank you very much. We can look at the peripheral leakage, through mask leakage, and all the other engineering parameters which are necessary for us and for the mask manufacturers. So in a nutshell, we have shown a framework that using generative AI, we can create thousands of faces. We show the fluid dynamics aspect that we can model these faces. So now our goal is to develop an agent-based epidemiological model. And by doing so, we hope to be prepared for any future pandemic. And this study will help us in policy recommendation for organizations like CDC, WHO, health professionals, and even for us. And this research is sponsored by NSF, and we are very grateful to NIR, which is National Artificial Intelligence Research Resources. We have got some GPU computing power from them. And I will stop here. Thank you very much.
Hello everybody. Good afternoon everyone. I am Shomik Shorkar. I am a grad student in Industrial and Manufacturing Engineering. I am working with Dr. Raghav Ganasambandam, and I am going to discuss today on my research how physics-informed machine learning can be leveraged to optimize advanced manufacturing processes. So let's dip in. Now, we know that advanced manufacturing, such as additive manufacturing, has high material cost. So it's actually crucial to achieve high quality product at the first try. But experimental data collection here is expensive and limited. Now, as a matter of fact, we actually want to predict the process parameters and we want to optimize these parameters. Let's say for an additive manufacturing process, the parameters such as, let's say, the temperature at the melt pool. So it is actually crucial because, for example, whether when the process is going on, if the temperature is in certain range, then we might get the high quality product. But if the temperature is not in the range, then we might see some defects in the microstructure. So inaccurate predictions can lead to defects and inefficiencies. Now, how to predict this temperature? So we have some experimental methods, like we will do the work again and again. We have the inputs and then we find out that okay, for this input we are getting this temperature. But it's really expensive because the additive manufacturing processes are expensive, and if the products are with defects, then we actually cannot do it again and again. Secondly, we can also use the traditional machine learning models, but the machine learning models actually use large data sets. But for the same reason, we will have to again need to have this data, and to do that, we will need to do the process again and again, but it's not feasible because it's time consuming and also expensive. And another thing that in black box machine learning models, we know that it's only taking the data and then it actually finds out the loss and then optimizing this. It's actually ignoring the physics here. And as the advanced manufacturing, we actually need the physical constraints too. And the numerical simulations such as FEMs are also computationally expensive here. So that's where physics-informed neural networks comes in. It actually integrates the physical laws such as conservational laws or let's say heat equations into the training. So it is both physically consistent and also data efficient. Now let's talk about the architecture of PINNs. We know that just like other neural networks, there are some inputs. Let's say for the additive manufacturing, the inputs are say X, Y, Z, the spatial inputs and also the time. And let's say there are some hidden layers, and then we have the output. So for this process, let's say the temperature is the output. Now, as we are integrating physics into here, we have the physical constraints. For example, they are like the heat equation or any partial derivative equations, and also we are taking some initial conditions and boundary conditions there. So we actually integrating this into the loss. So if the output is not aligning with the physics, then it is adding the loss. So that's how we are actually optimizing this, and then we will get the output. So here the PDs can be used, and also the optimization methods like optimizing the loss. Now in manufacturing, here we get from PINs, we predict process parameters from limited data because we can have some collocation points, and from there we can predict the output. It's it ensures physics consistent predictions and also reduces computation times compared to other numerical simulations, and also optimize process conditions to reduce defects. What are the benefits? There are no need for extensive meshing like FEMs. It generalizes better to unseen scenarios because as there are physics constraints are integrated, then it's actually does better in unseen scenarios. And also in PNNs can rapidly evaluate how variations in input parameters impact the manufacturing process. Like if there are variations there, it does not just take the whole process again. It actually can do this fast. Now, what can be the future works on this? PNN models can be improved for more complex geometries and also multi-physics problems. And we will have to address computational challenges in training PNNs efficiently because sometimes it actually does not work that good. So, if you are also interested, you can do some research on that. And also, I have plans to do further. So, to summarize, what we know that manufacturing optimization of the parameters require accurate. We need accurate parameter prediction to reduce the defects, and traditional methods have some limitations. So PNNs provide a powerful alternative, and as it's physics consistent and data efficient for learning for manufacturing. So that's it from me. Thank you everyone, and if you have any questions, ask me later. Thank you.
Hello everyone, my name is Yuexin and I'm a PhD student at the Math Department. Today I'm going to talk about image segmentation via row extraction with neighborhood pattern severity measure. It's a project in the directed reading program in Math Department, and I mentored an undergraduate student, Caleb Stewart, since last October. And I'm glad to share that our work was get accepted from FLMA conference yesterday, and he is going to present those work in details in the coming weeks. And I will first introduce the row extraction via neighborhood pattern severity measure, and then I will apply those methods or those measures to the image segmentation as an application. So the row extraction problem is to determine the representation of a network by a smaller structure graph. For example, for the community structure, we think that if nodes are connected closely to each other, then we put them into one groups. And we think the interaction between the communities are very weak. Then we can use like smaller graph to represent those structures. We can just use one node to represent one group. Okay, I won't jump, let me just explain. And we can always use a matrix to represent this graph. If we think a node I and a node j are connected with an edge, then we will just put number 1 as a matrix Aij, and if they are not connected, we will put a 0. Then we can always represent a graph with a matrix. For the weighted graph, we can put the corresponding weights replaced by the weight 1. So potentially, we think the adjacent matrix will have those block structures, but the original matrix may be like this. We want to swap some columns and rows to find out those block structures, which means to find out this smaller structure graph. And the row extraction problem can also detect non-community structures like bipartite structure, such that the nodes inside the groups have very weak connection, but the nodes between the groups have strong connection. And then to solve the row extraction problem, we will build up some similarity measure based on the matrix we have, and then we will use the clustering algorithm applied on the similarity matrix. And the neighborhood pattern similarity measure defines two nodes to be similar if they have similar neighborhood patterns in common. So for example, if we look at this pattern, those two black nodes have the same point-in nodes, then we think they are similar. And also those two nodes have like two point-out, this is point-in neighbors, and we also think they are similar. So this is like the neighborhood pattern of length 1. To calculate the number of those target nodes between every pair of source nodes like those of length 1, we can mathematically use the matrix we built using matrix A, use A transpose plus A transpose A to represent the number of those. Then for any length L, we can always use a recurrence to find out the number of common target nodes. So far we have a number of matrices such that each matrices represent the number of common target nodes with length L. Then we can have a weighted sum of those number of matrices and define as the neighborhood pattern similarity measure. So we have a matrix S, which is n by n, and each entry of this S represents a similarity score between two nodes. Based on this recurrence, we can also rewrite this formula in the recurrence formula. And the limit is the similarity the neighborhood pattern similarity measure. And there's a very good property of this S. That is why we can use this S to extract the nodes in each group. So for an ideal case of a graph, such that all the blocks of the adjacent matrix will be either all ones or all zeros. This is an example of an ideal community structure. If we can find out the eigendecomposition of this Sk and then write it as the factorization of this S, Sk or the limit size S, then the rows of those VKs have precisely R distinct elements. R is the number of groups we have. Like here, we can write this as VK transpose, and the first several rows are the same, and the second several rows are the same. So those same rows represent one group. Now we can represent each group as a point in the Euclidean space. For example, here R2. Let's quickly visualize it. So this is an ideal case of the community structure. So first, the several nodes are inside one group. The second several nodes are inside another group. And if we plot those coordinates, we can find out the nodes inside this group just as one node, as one point in the R2. And this point represents all the nodes in another group. If we add some noise, we can still see two separate groups in the R2, and then we can apply any clustering algorithms in the Euclidean space. So actually, in practice, to find out those groups, we don't have to formulate S. We only need to find out this V. And for the undergraduate student, he can just compute this V by eigendecomposition. But for my research, we compute this V to solve a optimization problem on the manifold. And after we find out this V, we think each row is a coordinate in the Euclidean space, then we can run like K-means plus to find out those groups. Then we have the application on the image segmentation. So suppose we have a picture like this, and for those pictures we have pixels. We think each pixel is a node. Then we can build up a weighted graph based on those nodes. We will build up the weights based on the pixels, just calculate this way. Then here, we can set different sigma. Then we have our weighted urgency matrix. Then we can find out this V by the weighted urgency matrix using the previous recurrence or use the algorithm. Then we can run clustering algorithms like here K-means plus to extract two groups. And then we just set one group as black, one group as white. Then we can have the image segmentation result. And here it's just I set another result to have a weighted case. Set some threshold of this W. If it's above the threshold, we say the weight is 1. If it's below the threshold, we think the weight is 0. Then we can have a weighted case, and if I commute the original A to have the reorder A such that the nodes here inside one group, nodes here is another group, so we can clearly see block structures. And here is another example of another image. And actually, he did more experiments, and he just used his own picture to get some result. But here, just do some simple testing for today's talk. So briefly speaking, we can represent an image with a weighted graph, and the graphs can be translated to the matrices and solve it directly and mathematically, and we can apply restriction via neighborhood pattern similarity measure to the matrices and for the image segmentation. And that's it.
All right. Hi, everyone. My name is Jake. I'm a second-year undergraduate studying computer science. and I've been working with my research mentor, Dr. Boriga, for around 5 months now as part of the Europe program. And today I'll be talking about some of the work we've done so far. So, quick background on the GluX experiment. GluX stands for gluonic excitation. The core of the experiment is shooting a beam of photons at a target of liquid hydrogen. And the rest of the experiment is just a very big detector setup, essentially, for detecting all of the various particles that are produced in that photoproduction reaction. Specifically, there's 2 types of detectors. There are drift chambers for detecting charged particles, and there are calorimeters for detecting photons. Detecting photons is very important because certain particles are very unstable and they will decay long before we can reach them or measure them in the detector. So our only way of knowing that they're there is by measuring their decays. So as I mentioned, some particles will decay to photons before we can measure them. So in order to figure out what those particles were, we have to make educated guesses based on those photons that we can see. An example is that, for example, a neutral pion and an eta particle will both decay to 2 photons, which leaves us in a bit of a bind identifying what the original particle was, since all we see are those 2 photons, and we can't make a conclusive decision about whether it was a neutral pion or an eta. So we use conservation laws and a few other things to make guesses about those particles' identities. And then we assign a chi-squared value to describe how confident we are. The lower the value, the more confident we are in our identification, and the higher the value is, the less confident we are in our identification. Practically, this can be a challenge for physicists because a physicist might create 2 different data sets, each for a different hypothesis. So for example, again, the neutral pion and the eta. But since both particles can be reconstructed from 2 photons, there will be many events that are identical between these 2 different data sets. But in reality, in the actual experiment, each of those identical events can only have been in one or the other data set, and we have to try to identify which hypothesis better explains the case that we saw. So this is an example of such a data set with exactly 1 matched event. We can see, essentially, this is very oversimplified, but what the tool that I wrote does is it loads all of the events in each data set into a, essentially just exactly what you see here, and will define one data set as the primary hypothesis, which is an arbitrary definition. In this case, it's the neutral pion hypothesis, and will then look through the alternative hypothesis, identify the chi-squared value for a matched event in the secondary hypothesis, and then copy the primary, I don't know if you can see my mouse, the primary data set, and then append a new column, which is this one right here, containing the chi-squared value from our alternative hypothesis, which essentially just collates all of the data we have into a single place, which a physicist could then run through and perform an analysis on. In this case, you could see the chi-squared value under the eta hypothesis is significantly lower than under the neutral pion hypothesis. So a physicist would be pretty would be able to confidently say that this particle is better explained under the eta hypothesis. So as an example of this, on the bottom left here, this is essentially what we want to see if we plot our eta candidates, which is a very nice clean signal right around the eta mass here, 550 mega electron volts. But this is a simulation. This is not what we actually see. What we actually see in our data when we plot a eta candidate mass distribution is that we have this background on the right side of the signal, and then we have also this very large background on the left side of the signal. And what the tool enables the physicist to do is plot each hypothesis, or plot the distribution which each hypothesis broken down, which in this case, if we plot the neutral pion hypothesis, we can see that there's almost no, or essentially no contribution to this big eta signal, which we would expect because eta particles will obviously be concentrated around the eta mass, whereas a neutral pion will not. But what we do see is that the neutral pion hypothesis contributes a lot to this big bump on the left side that we don't want to see at all. So a physicist would be able to look at this graph, determine that these events are better explained under the neutral pion hypothesis, and then cut them out of their data, which would reduce this spike on the left. There's obviously still, even in our good events, the orange here, our good eta events, there's still that same background, which would hopefully be explained by running this data set across several different hypotheses. Here, for simplicity, we only have 2 hypotheses, but theoretically, we could run this over many more. So in conclusion, the tool lets us break a distribution into all of its constituent hypotheses, or based on how well they conform to the physics constraints that we place upon them. And that breakdown gives us a better way for removing background for our data and also seeing exactly where that background is contributing. We still need to do a lot of further testing across different reactions, and we still need to compare essentially how well this tool does versus other more traditional tools for removing specific backgrounds. That is all.
So, hello everyone, my name is Lawrence and I'm a graduate student from the Department of Statistics, and today I'll be presenting using LLMs to perform information extractions on biomedical literatures. And to motivate us to think about this problem is let's consider the amount of paper that are being published every day. In order to help the researchers to be able to find the information that they are interested in, it's impossible for them to read every new paper that are being published every day. So we need a systematic way to help the researchers to more quickly to navigate the information that they are extracted. And the previous solution for this problem is to use a fine-tuned deep learning model to perform an entity recognition to extract the information that we're interested in biomedical literatures. And for this method, it's since it's built by training on a specific data set, and it with the capability of the model, it'd be able to learn the data set pretty efficiently and effectively. So the effort score of the models are relatively high, but there's also a problem for this approach is that when we try to use this model that we trained on a biomedical literature, when we try to apply this model to other domain that's not related to biomedical, then it will have a pretty bad result because of overfitting. And so here we see the opportunity of using LLM to perform this task because of the nature of LLM are being pre-trained on a vast amount of general data. And so we see that this could be a potential solution to tackle this problem. And the dataset that we are using for this study is the same dataset we use on the Lickline challenge in order to have a better comparison for these 2 different methods. So the dataset consists of 500 biomedical abstracts from PubMed, and the annotators annotate all these different articles into 6 different kind of entities. And to fully understand what kind of prompt we should be using for this specific task, we designed 2 types of prompt. The first one we designed is that it consists all the very detailed all the structures, instructions to give the LLM to fully understand what we're trying to do here. So it has the task description, and we have the entity markup guide to control the what's the output we are expecting to get. And also we give the definition of what a disease is. And we also give the annotation guideline that we use by the annotators when they annotate the training data. And also we also provide a few short examples for the large language model to understand what's the task they're actually doing. And the second prompt we design is relatively shorter and much more simple. We start with a simple question asking whether if this sentence contains disease or symptoms, and we also provide the markup guide to in order to control the output format and also give the input sentence. So we use three different types of LLM. The first one is Cloud, and the second one is GPT, and the last one is Llama. And as we can see, they did pretty good, and they're able to capture most of the information that we were interested in. But comparing to the result from our previous solution using Roberta, it's actually have a pretty big gap between those two methods. So in order to fully understand what actually causes these errors, we decide to look into all the errors that they made, and we find that most of the errors actually caused by the annotation quality. So most of the error was caused by there's a contradiction between the annotation guideline comparing to the training data itself, such as in the annotation guideline, there's specifically sets that do not annotate certain words, but in fact, turns out that in the training data, actually the experts actually annotated those words. So when we feed the annotation guideline to the LLM, when it uses the annotation guideline, and it will it conduct a contradiction between the golden standard and what's the actually what their understanding of the problem is. And the second one is the true label also have some questionable labels. The first one, there's a case that our team and all those 5 LLMs agrees on is the true label should be spatial learning impairment, but turns out that the true label only labels learning impairment as a disease. So there are several more cases like that. And after we eliminated all these different kinds of error, we found that there's only a very small amount of errors that only because of the LLM didn't able to understand the context or hallucination or other steps, potential unknown cause for these errors. And so we see that for this problem, it's very crucial to have a good quality annotation, and also we also summarize that LLM is actually a reliable solution for this problem. And this is the reference for the study and this my presentation. Thank you.
I want to thank our keynote speaker, Dr. Gao, and all of our student presenters for their thoughtful and insightful presentations. And I also want to recognize Reagan for all of her hard work in organizing this symposium. This is the second one of these that she's organized. And to all of those at the libraries who have collaborated with us to make this symposium happen. And I will say for the speakers, we are passing out some little thank you gifts for all of you. And if you could stay for just a few minutes after my remarks, we're gonna get like a group photo of everybody. All right, so machine learning, artificial intelligence, and data science are widely discussed topics in society today. AI and machine learning are already in use across many industries, such as healthcare, finance, education, and more. Furthermore, the advent of large language models, which surged into prominence with tools such as ChatGPT, has really revolutionized how we learn, work, and interact with the world. However, these developments are not without their challenges. As we heard today, the growth of LLMs come with challenges in terms of infrastructure and computing power. Security and privacy concerns are also key considerations when we think about data and how we train and use AI. And as these new technologies develop, society will need to balance the benefits that AI and machine learning bring with these important structural and ethical considerations. As we saw today, researchers here at FSU are increasingly finding new ways to apply AI and machine learning models to solve problems across a wide range of disciplines. Dr. Gao kicked off our symposium discussing different ways to produce more efficient large language models. We heard about applications in medicine, such as using prompt-based LLMs in biomedical NER, and work that is utilizing machine learning for optimizing mask design and preventing respiratory diseases. We heard about how machine learning can be used to improve manufacturing processes, the analyzation of images, the identification of reactions. So today's symposium has really demonstrated that AI and machine learning is not limited to specific areas or topics. It's really something that we can apply across disciplines, and it allows us to think about important research questions in new and innovative ways. As you leave today's symposium, I hope you're inspired to think of ways in which AI, machine learning, and data science are affecting the world around us. While there are still many questions and challenges that lie ahead, there is no question that these new technologies are and will continue to affect our lives in many ways. I encourage you to continue these conversations with your colleagues, with your peers, and even those you have met today. And so again, thank you all very much for attending. I hope you found this inspiring, thoughtful, and we look forward to seeing you again at future events. Thank you very much.